Hi, I'm Alex Williams. You've seen me in such fine quality, epic chemistry educational videos as Kinetic Molecular Theory and Basketballs. What's the connection? And do gas particles have an impact on how basketballs bounce? Part 2. Okay guys, for this segment we're going to be looking at the kinetic molecular theory. Okay, and in looking at the kinetic molecular theory, we're talking about why is it that the ideal gases, they're behaving the way that they do. Okay, and of course one of the things is because it's a theory, it's not a law, it's not a hypothesis. Scientists try to come up with a model to explain how God's creation behaves, because that's really, if you think about chemistry, it is the study of matter, and it is a study about God's creation and how He does things. Okay, so there's a few assumptions that need to be made, and yes, we can talk about the jokes made with the word assume. We're not going there, but think about this. The assumptions will help simplify the theory, but it doesn't work when we talk about real gases. Then again, we are talking about ideal gases here. So number one, the particles are so small we can ignore their volume. Okay. Number two, particles are in constant motion and their collisions cause pressure. Number three, the particles do not affect each other. Think ideal gas law. Okay. They don't attract and they don't repel. So Paula Abdul, you're out of there. The average kinetic energy is proportional to the Kelvin temperature. Well, that's kind of reasonable, okay? So in other words, if the Kelvin temperature is high, then we would expect more average kinetic energy as a result of it. Because if you think about it, temperature represents heat energy, or the amount of kinetic energy that's there, the average kinetic energy. So it's not a completely crazy idea. Now, number two, the appendix 2, I am not going to worry about that. This is the basic kinetic energy equals 1/2 mass times volume squared formula. I'm not going to sit there and really make a big deal about it, except the average for kinetic energy is 3/2 times R times T. Now R, there is another variable, another value R that's there. We'll get into that for a few minutes, okay? When we look at something like the letter U, this is now our first exposure to the letter U. It is referring to the particle velocity. Whether it's hydrogen gas or chlorine gas, it doesn't matter. Remember, a particle covers quite a few things out there, okay? It covers quite a few atoms or molecules dealing with gas, because that's what this chapter is related to. So the bar over the U is the average particle velocity. The bar over U squared is the average particle velocity squared. So when we talk about the root mean square velocity, this is what we mean by this, okay? So wait a minute, the U basically means how fast is the particle traveling, right? Okay, because we make an assumption. We make several assumptions about this happening. Now this really should be combined. If we take these two separate equations here, okay, and combine it here, we do get a new formula there for it. And that formula, I'm going to go ahead and write this down. That's going to be a whole lot simpler for us. And here's the formula in question. This is the formula you need. This is for the root mean square, okay, velocities. So you've got mu, and you got the little ms, is equal to the square root of, okay, 3RT divided by capital M. Now, here's the thing, and this does get a little confusing. The capital M here is not talking about molarity like we did in the last chapter. I know this is frustrating. I'm not the guy who came up with this.
Okay, but for now, our capital M here refers to the molar mass in kilograms per mole. Now, some people might be thinking, wait a minute, kilograms per mole? We've never done that before. You're right, we haven't. But stop and think about it for a moment. We've always worked with grams per mole. And if you think about it, a kilogram is 1,000 of those tiny grams. So when we're looking at the molecular weight of something, we already know the grams per mole. All we have to do is 1, divide it by 1,000, or 2, we move the decimal place to the left 3 places. So what would happen is you'd get a much smaller number by a factor of 1,000. So for example here, if we look at kilograms per mole of, let's say, oxygen. Oxygen atoms floating, okay, rephrase that. Oxygen, O2, okay, we know that O2 is 32 grams per mole, right? We know that is what O2 is equal to. This is what we're normally doing. But in this case here, with the big M, since we're looking at the molar mass, why in the world are we doing this? This is only done when we're working with these gas laws. So you would end up shifting it 3 places to the left. 1, 2, 3, or 0.032 kilograms per mole. So you definitely have a smaller number. But remember, you also have a bigger unit because a kilogram is bigger than a gram. Now the R also has a new value. Don't freak out, okay? The idea is pay attention to your units right here. In this case here, we're looking at joules per Kelvin times mole, okay? That's the key thing. Joules per Kelvin times mole. So that's what we've got going for us. So when we are looking... Go away. Thank you. Okay, so when we are looking here, okay, we're going to be calculating how fast those gas particles are actually traveling in some kind of a container, okay? And actually, wow, they get to be pretty fast. But the velocity is still going to be in meters per second. Okay, so why don't we go ahead, let's do an example here. We can calculate the root mean square velocity of carbon dioxide at 25 degrees Celsius. Wow, where do we go with that? I'm glad you asked, because you know, excuse me, we have the know-how. So we're looking at CO2 gas. Okay, we're looking at CO2 gas and it's traveling through the room. And we're looking at how fast is it traveling at 25 degrees Celsius. Okay, that's about room temperature, no big deal. Okay, but what are some facts that we know? Well, we know that R, we know the value of R. The value of R, based off of our last thing, they gave us as 8.3145 joules per Kelvin times moles. Okay, so we have that. We also have the temperature. The temperature, they gave it to us in Celsius, but remember we have to change it to Kelvin. So that's going to be 298 Kelvin. Okay, so far so good. And then we have M. Okay, and that's going to be in kilograms per mole. Well, what do we know about carbon? Carbon is about 12.01 grams per mole, and oxygen is 16 grams per mole, so we got 16 times 2 is 32, plus 12.01, that makes us 44.01 grams per mole. But hey, we can divide it, right? We can divide it by 1,000 or move the decimal place, so we'll already have here 0.04401. Okay? So this is what we have. So this is our information that we've been able to piece together. Okay, how does this all fit? Well, remember, we're using the square root formula, right? We're using that square root formula of 3 to RT over M will get us our root mean square formula. Our root, try that again. It's a little late, okay? And it's a tourist day for homecoming week, okay? So we're looking at the speed. How fast are these particles traveling? So this is what we have. I'm thinking now, is it time to plug it in? I would say so. And here we go. So we got ourselves a nice big square root of 3 multiplied by 8.3145 multiplied by 298 over 0.04401 kilograms. Okay. In order to spare the time, okay, I'm going to tell you right now, our final answer is 410.97 meters per second. Now, of course, the $64 question is what were the measurements that they gave us? Okay, there are how many significant digits or how many sig figs are we looking at here? You know what? I'm going to go ahead and I'm going to stick with, if I stick with 1, then how do I handle that? Because I want to make sure Odell doesn't pop that blood vessel, right? Okay. Well, if we only got one significant figure, how do we handle it? Well, let's see. We can put this in scientific notation. 4 times 10 to the second meters per second. Ooh, you thought I couldn't pull that off, did you? Surprise! You can do that. And that's how you can actually get away with that in terms of the sig figs. Okay, any questions? That's right. You can't ask those questions. But hey, let's go ahead and let's do another one. Okay, and the next one that we have here is the root mean square velocity of hydrogen at 25 degrees Celsius. Woo! Okay, so what do we know? Well, we have our R is equal to 8.3145. Our temperature is equal to 298 Kelvin, because remember, it's 25 Celsius plus the 273 to convert. Now, we also have our M. Well, in this case here, remember, we're looking at H2 gas. So that's going to get us a big whopping 0.00202 kilograms per mole. So this is what we have. And you're thinking, wait a minute, how did you get this? Well, remember, 2 hydrogen atoms, each one being 1.01 grams per mole, times 2 is 2.02, and I went 1, 2, 3. Oops, I'm sorry, it was here. 1, 2, 3. That's what I did. So I changed it to kilograms per mole. Okay? Now, let's go ahead, let's plug this bad boy in. Let's see how this works in our cute little formula. So we're going to have the square root of 3 times 8.3145 times 298 over 0.00202. Now remember, we don't do the rounding until we come to the very end of the whole game. So in the end here, our final answer, calculating all this, we would end up getting 1,918.276 meters per second. Whoa, man, that's fast. Absolutely. But stop and think about it for a moment for those gas particles. If they're having the same amount of energy, then you start looking at kinetic energy, mass and velocity squared times 1/2. then the question you gotta ask yourself is, well, wait a minute, does that mean that the lighter particles actually travel faster than the heavier ones? You guessed it. You got it. Okay? It is true. Those particles travel faster. The smaller the particle, the faster it will travel. Okay? That's just the natural law of things here. But to make sure that we're okay with our sig figs, and they did say, they gave us a 3. I'm going with the 3 here for the measurement. So I'm going to go ahead and once again, I'm going to look at 19.18. So I'm going to say 2 times 10 to the 3rd meters per second. That's how it's done. Okay, is there anything else beyond that? Well, at that point, there's a couple of other things, but I think, let me see, do I want to go any further on this? Yeah, I mean, I've got a few minutes, so I'm going to go ahead and let me finish up here, okay? So when we look at the range of velocities, okay, it's the average distance the molecule travels before crashing with another molecule. That's what they call the mean free path, and it's really small. It's, if you think about the distance, it's near 1 times 10 to the minus 7th meters. So they don't travel very far before they go crashing into each other. Now, remember that the temperature is an average, and you have molecules of many speeds within that average. Okay, and we can talk about a graph called a velocity distribution. If we look here, excuse me, here's a graph, the number of particles versus the molecular velocity, and you kind of notice at 273 Kelvin, or 0 Celsius, the highest number of particles seem to have a fairly low speed, okay? But when the number of particles goes down, guess what? They tend to go a little bit faster. Well, why is that? Well, remember, there's less particles that go crashing into each other as well. So they can actually travel longer distances in the process. Think about that way. Same concept here. Here we superimpose another thing here where we look at the 1273 Kelvin. Okay? And again, if you look at it, compare it with this, and here we go, another 1273 Kelvin, but guess what? This time you've got less number of particles, but look what's happening here. You've got more of them traveling at a faster speed. Just something to think about as we wrap up. Velocity, the average increases as the temperature goes up. That's the summation of those graphs. The spread increases as the temperature increases as well. And with that, ladies and gentlemen, I hope this will give an explanation as to why do basketballs bounce the way that they do, and why is it important to properly inflate the basketballs, unlike in the football league. Deflate gate, baby! This is Alex Williams, hard hitting, in your face. Have a nice life.